Good morning, good afternoon, and good evening. This is a tutorial on structured credentials, specifically an overview of a structured credential and how you would use them in the Trusted Digital Web project. To give you a little bit of context without going too far overboard, the Trusted Digital Web is an end-to-end, standards-inspired, verifiable, fully decentralized object workflow platform. It's intended to be the next generation of the World Wide Web running on top of the internet. The standards roadmap for the Trusted Digital Web is based on DIDs and verifiable credentials and enterprise data vaults, but the project is taking a very specific strategy of just make the platform work, make it work better, make it work right. So in the beginning, the architecture, the design, and the implementation is inspired by these standards. It will contain all the information elements required to support those standards, but it might not be element for element compatible. And that's on purpose, that's deliberate. In the end, what FDOs or fully decentralized objects are used for is as a strongly typed object model for business documents. For the storage of business documents in subledgers inside a wallet, for use inside the Trusted Digital Assistant, for the transmission and exchange of those trusted documents. Examples, of course, being purchase orders, invoices, waybills, and delivery confirmations. On the right there's an overall architecture for the Trusted Digital Web project, an 8-layer architecture reference model. We're not covering that today. Where today's discussion of structured credentials fits in is within this green triangle. We're using something called the Microsoft Trinity Graph Engine and the Trinity specification language, which enables automatic code generation of objects, of messages, of request response protocols, public and private micro services, their actual implementations, skeletons for the microservice endpoint handlers, persistence models to memory, persistence models to disk, and support for the link query language. But let's go on and discuss structured credentials a little bit more. And in particular, the metaphor to help programmers understand and program against structured credentials on the Trusted Digital Web. The metaphor is an envelope. An envelope has content. An envelope can have a packing label. And the envelope can have a seal. These are the 4 elements that comprise a structured credential. So we start off with the credential envelope, a container, if you will. Inside the credential envelope, we have the envelope content. That's the actual credential itself. You would know it as the ID field, the @context, and the claims themselves, the name value pairs, and potentially, if this is a bound credential, the ID for the subject. Once the envelope content, the credential, has been placed inside the credential envelope, you can attach a packing label. The packing label is I say just metadata, but it's some specific elements of metadata that aren't formally part of the credential or the envelope content itself. So we put the credential, the envelope content, inside the envelope and close the envelope. The only thing we have left is the packing. So there's the credential envelope, the packing label, and then the last thing that we want to attach to our envelope is a seal in verified credential nomenclature. This is the proof. So we have an envelope. We have contents inside the envelope. We have a packing label to represent the metadata attached to the content in the envelope, and then we have a seal. Using the Trinity specification language to provide an abstract design language, an abstract way of defining these elements of a credential envelope. We start off here in green at the top. You can have a set of claims. So this is the set of claims that are part of the postal address schema on schema.org. Street address, post office box number, address locality, address region, address country, and postal code. So that's just claims. Those are name value pairs. And of course, they're tightly scoped in terms of all being strings. This is perhaps a bad example. I could have date time fields in there. I could have bit fields in there. I can have structures of structures, and we actually see that down below. We can see that TRA postal address underscore claims in the top green box is actually used to define the envelope content. So the envelope content is a structure that is pervasive across all credentials, across all structured credentials on the Trustful Digital Web. They all have these 4 parts. So here we can see that the TRA postal address underscore claims is used to data type the claims element of the envelope content. And if you're familiar with verified credentials, you can see that we have a UDID, which is just our nomenclature for a conventional DID. Here we can see we're using a .NET list collection of strings to define the different contexts that may be applied. We have the credential subject DID. So this is the ID that's inside the credential subject element on a bound credential. And it's optional because we can have both bound credentials that are bound to a subject and unbound credentials. And we actually make a lot of use of unbound credentials on the trusted digital web for complex objects like invoices, where there is no single subject that the credential is an extension of. So we've got the claims. That comprises our envelope content. Let's take the envelope content and stick it in the envelope. How do we do? There we go. So we take that structure, the TRA postal address underscore envelope content, and we use it to type an element within the envelope called content. Nice simple layering model, a nice easy model to explain to developers. Next, we take that envelope and we're going to use it to create something called a cell. So here we see the envelope element within a TRA postal address cell. Cell is a bit of a legacy term. Part of the Trinity graph engine automatic code generation capability is the ability to create cells. And cells, think of it as a unit of storage in your wallet. And in case of the Trusted Digital Assistant, it's a unit of storage within a subledger within the wallet of the Trusted Digital Assistant. So when we look at all 4 of those elements together, the content, the label, the envelope itself, and the seal, those we collectively call a cell. And again, it's just a name for legacy reasons. Next, we'll highlight 2 elements, one of the envelope and one of the cell, that are globally defined for all structured credentials. So the concept of the packing label. And you can see there in brown, it's used to type the label element of the envelope. So what's an envelope? It's the content that's inside and the label that's on the outside. Lastly, what we have now is really an untrustable credential. It doesn't have any hashes or signatures. It's not connected with a verifiable data registry. So the way where we put that information is in the envelope seal. That's the red wax seal that's on the exterior of the envelope. So that is the Trinity specification language for the conceptual model for structured credentials, but it's also an operation model. I can run that through a compiler and then generate an entire C# project using .NET Core 3.1. It'll run on any platform. It performs or supports automatic construction of all of these elements, automatic persistence into memory, automatic persistence to physical storage on the device. And I can take any of these elements and use them to be part of a message that is sent either synchronously or asynchronously over HTTP or not over HTTP between agents. And the Trinity compiler also automatically generates the agents themselves, what I referred to as the public and private microservices from earlier. So we've already talked about cells. So here, just some of the common structures that were used on the previous slide. So we have a packing label. That's just an example of some of the stuff that might be in the packing label. This is a little bit of fluid right now. Things like the credential type and the version of the credential. The trust level. So trust level is unique in that you can set the trust level, and when you go to persist the object, it'll automatically sign it, hash it for you, automatically sign the hash. And if the trust level says that it's supposed to be verifiable, it will be recorded on the verifiable data registry. I kind of skipped over some additional fields in the previous slide, but you can also choose to crypt or decrypt, have encrypted or unencrypted versions of your content. That's separate from the trust level. Down below in the kind of orange, there's the envelope seal. So again, depending on the trust level that's sent in the packing label. Any of these optional fields might be filled out. The digital hash, the signed digital hash. There's the notary stamp, to be determined some sort of link into the verifiable data registry if the trust level is verifiable. And most of the structures have a comment field, either a single comment or perhaps a list of comments, so that you can comment your credentials just like you would comment code. So here's a specific example where we're going to talk about postal addresses. So there's the claims that we talked about before. And we're going to look at how do we actually program against the automatically generated C# code. The only handcrafted code is the code that you're going to see on the next slide. The rest, all the underlying classes were automatically generated. So here we can see how we're using that postal address definition from above. We start by creating a new instance of the cell by passing in a unique integer ID. We create a new instance of the envelope and a new instance of the envelope seal. Next, we need to populate the claims. So we take postal address underscore claims, and we initialize the street, the post box, the city, the region, the country, and the postal code. If we go back here quickly, can't do that in this recording. So we just take those claims and then we create a content envelope. We take the DID, so now we're getting into the formal specification of the credential. We take the DID, the context, and the claims. That should be very familiar to those of you familiar with the construction of a verifiable credential. Now we need to attach the label to the outside, the metadata. And so this is a notarized credential. It needs to have a signed hash. That's the level of the trust level we're supporting for this. It's not encrypted. This is the name and then an example of the comment. So at this point we have created an envelope, a cell. We've created the envelope here. We've put content in the envelope here, and we've put a label on the outside of the envelope here. Next, we want to seal the envelope. So here I've kind of dummied it in because I haven't implemented all the trust level code yet. But here's when we seal the envelope, we need to compute the hash, sign the hash, and do a few other things. And so a helper method is needed in here to actually compute the hash based on who the current user is, what their UDID is so that their public key can be looked up, so that their private key, public key pair can be looked up from the key management agent, if you went back to the second slide in the diagram. And then we can save that into storage. So global local storage, save the postal address cell by passing an instance of postal address. So I think that for C# developers, for traditional developers, heaven forbid non-JavaScript, non-JSON developers, I think they'll feel quite at home with this approach. So there we have it. We have trusted structured credentials. We have an envelope. We have content in the envelope. We have a label on the outside of the envelope, and optionally we can add a seal to the outside to support the different trust levels. The envelope, the content, the packing label, and the seal. So just a footnote, not directly related to everything we've seen above, but recently there's been this discussion on the W3C mailing list about, for example, the primary color verifiable credential and whether there's a verifiable credential or not. I don't have an example in this deck. But it was an example of an unbound credential, and it's an unbound credential because it does not have an ID field as part of the credential subject. As one person said, it's simply data signed by the issuer. What most people are familiar with are bound credentials, the default meaning of a VC. So it has context, it has a credential ID, it has a list of credential types, both sides. It has a collection of credential subject claims, name value pairs, and one of those claims needs to be the ID of the holder. The ID of the holder, which is equal to the subject. Both of them need a proof that's issued by an issuer. Both are held by the holder. More specifically, bound credentials can only be held by the holder. They're bound to the ID value of the subject credential. And that's just part of the verifiable credential spec, the verifiable credentials specification, so that if verifiable presentations are to be created from a verifiable credential, they need to be bound to that particular issuer. Again, on the right side here, unbound credentials are not bound to any subject. The trusted digital web actually uses these a lot on to represent complex credentials like purchase orders, invoices, waybills, delivery confirmations, things that are not natural extensions of a subject, not natural metadata or credential data extensions of a subject. So this is a rather new concept, and of course it builds on top of what we've just been looking at. So thank you for listening to this talk about structured credentials.